Welcome to the video on Diels Alder reactions, stereo and regioselectivity. I wasn't exactly sure what the best way to convey this information is. Honestly, in the classroom, what we'd be doing is manipulating a lot of model kits and kind of supplementing that with me writing a bunch of things on the board. So I just kind of went with the bigger board surface. If you think these kinds of discussions would be a little more helpful using that kind of like my camera pointed directly down at my Sharpie writing on pages and stuff like that, just let me know. But anyway, we're going to start talking about really stereo selectivity. And keep in mind, anytime you have like a stereochemical consequence, right, it's important to recognize that stereoselective reactions will only do one of those. And the reasons for that almost always have to do with mechanism. And kind of some sort of like necessary arrangement of starting materials. So we're going to do the exact same thing that we talked about, right? We're going to remember that a Diels-Alder reaction requires some sort of diene, and I'm going to use a really specific diene in this case, right? I'm going to use this thing called cyclopentadiene. You'll notice that, you know, Pac-Man's mouth is, or what I called Pac-Man's mouth in the case of the diene, is definitely locked in that S-cis conformation, right? We talked about the fact that S-cis puts the double bond on the same side. Let's redraw this so it looks like somebody that knows what they're talking about actually drew it. And we're going to react this with just kind of a generalized dienophile with electron withdrawing groups. Keep in mind, we talked about requirements in both of these reactants, and that electron withdrawing groups are pretty much required for a Diels-Alder reaction to happen, and those include things like halogens, like nitriles, like carbonyl-containing species and such. And then this guy, right, this diene, it could have some sort of electron donating group on there. It certainly proceeds a little faster if it did. I guess technically you can consider this one little CH2 here somewhat electron donating. So what we're going to do is we're going to recognize that kind of one of the amazing things that a Diels-Alder reaction does is it puts all kinds of really awesome three-dimensionality into a product. So what I've tried to do is I kind of grabbed two different model kits and I stuck a bunch of stuff together. So what I have here is obviously this cyclopentadiene, and then I have this kind of generalized dienophile that these red spheres are going to represent electron withdrawing groups. And so keep in mind that our Pac-Man, right, we always have to put the meat in the sandwich, right? Those electron withdrawing groups need to go towards Pac-Man's mouth. But what really is going to happen here is that I'm really going to have these two kind of that paracyclic reaction, right? It's really like these things are kind of like two pieces of bread that are adding on top of one another. Man, maybe I should eat something. I keep having sandwich analogies here. And so when we do that, right, I want you to imagine that as you make the bond, that this thing kind of flips a little bit, right? And it's kind of hard to do without you guys actually holding it in your hands. But as that happens, this CH2 is going to get kind of forced up, right? And so what you end up with is a structure that looks like this, right? And what I'd like you to notice is that what we have, if you look at the six-membered ring, right? There's my six-membered ring, right? In this plane right here, there is almost I guess a U shape, right, for that six-membered ring and the electron withdrawing groups, right? That is going to be something that's really important, and that is called the endo product, right? The stereochemistry of Diels-Alder reactions is said to proceed with only stereoselective for endo products, right? And that's what they're talking about, this kind of, this end-on kind of sandwich, right, results in those things kind of being projected downward, so you get that kind of U shape. What doesn't happen, and I'll draw all this on the board in just a second, what doesn't happen is the XO product, or at least in these types of reactions, the XO product doesn't happen. In other words, the product that would have resulted from having our bonds form like this. And maybe I'll even include like a screen grab of kind of a little video here, and maybe I'll insert it here, so I'll pause.
So you've seen a couple of animations from this ChemTube 3D site. Unfortunately, I couldn't find the exact reaction that we were talking about, but what I did find was cyclopentadiene reacting with this as the dienophile. The only thing is that in ours, these electron withdrawing groups just aren't linked together, whereas they are in this one. So let's take a look at the endo transition state first. So here is the endo transition state, and I'm not sure if I'm going to be able to rotate this. Oh, I guess I can. That kind of shows that three-dimensionality. What you can see here is the fact that those electron withdrawing groups are kind of interacting through that little pie sandwich there. And then what will hopefully this animation will show when I click on this is we'll be able to see how those groups end up pointed downward and kind of what happens to the CH2. Whoops. All right, there's our product. And so that's how that particular set of bonds forms. Now, if this was going to proceed by the exo transition state, right, notice that those electron withdrawing groups are kind of pointed away from your diene. And we can see the Z that I was talking about for the exo product there. So this is the one that usually does not occur, and then the endo is usually favored. And so in just a second, when we return to the video lecture, you'll see that the consequence of these electron withdrawing groups having to be down here makes this particular group always facing in the other direction. So if this wasn't just a CH2, right, if this was actually something that was bonded out here, it would actually be pointed up, whereas all those electron withdrawing groups are pointed down. And of course this one, because that one's pointed up, that one must be pointed on the same side as the electron withdrawing groups.
And so when this were to form, right, this is not the type of product that we form, we would call that an XO product. Okay, so here is the result, right, of an XO type of attack here. And this is called the XO product, and this is the one that does not happen, right? This is what I kind of see when I first started playing around with these model kits, is I kind of see a Z, right? The electron withdrawing groups and that six-membered ring, they kind of look like a Z in what's called the XO product, right? And this does not form. The only one that forms is the endo product, right, where those electron withdrawing groups are here to form the U. So let's go back to that one and we'll try to draw it. Okay, so how are we going to draw this, right? And so first thing I'm going to do is I'm going to draw what it would have looked like if I did this reaction and was looking straight on the six-membered ring, right? Because that's an important view that we should learn to recognize. And it's important to kind of be able to translate what I'm about to draw in this like kind of three-dimensional manner into like a normal like non-bicyclic system, and you'll see what I mean by that as we kind of go on in this video. So first thing that I'm going to recognize is that this group, right, and the way I was just holding it, right, that little CH2 group is going to be coming out at me, right? And so let's start with the six-membered ring, and we're going to put that CH2 coming out at us with these solid wedges. You'll notice that those electron withdrawing groups, and this is important, right, are on the opposite side of this group right here that was held in Pac-Man's mouth, right? In that S-cis conformation, these positions where those things are pointed in, right, they end up on the opposite side from those electron withdrawing groups. Whoops, not electron donating groups, electron withdrawing groups. So this, right, both of the things that I'm showing are considered endo products, right? They had that nice little U. I could, of course, instead of drawing it like this, right, I could have drawn it a little bit more like this or like this, and that's something that you're going to see quite often with these bicyclic systems, right, which the Diels-Alder reaction are really good at producing. So this is going to be equivalent to that structure, right? And so you can see that kind of U there, right? We are not getting the exo product where this group and those electron withdrawing groups would have been on the same side of that ring, right? And so those electron withdrawing groups are not, up and to the right. They're very specifically down. Turns out that just about every Diels-Alder reaction, certainly the ones we'll be talking about, are endoselective, right? Which means that this inner position, right? I consider anything that's kind of pointing in like this inner, and anything that, I'll draw these in blue, right? Obviously there's an H here that in this case doesn't really matter that much. Those are considered, at least in the way that I think about this, as outer positions, right? And you'll notice that if I were to include those outer hydrogens on this structure, that outer position ends up on the same side as the electron withdrawing groups, okay? So let's kind of make one little change to this system, and then I'm going to get rid of the bridgehead carbon, right, this carbon altogether, and you can see how you can really be good at predicting kind of specifically which stereoisomers are possible in Diels-Alder reactions. Okay, so one minor change I've made is that now we have electron withdrawing groups, which are still necessary for promoting the Diels-Alder reaction, but now they're on opposite sides, right? Now it's a trans or an E for entgegen, right? So you'll notice that now, no matter what I do, right, one of these electron withdrawing groups has to be pointed in and one has to be pointed out, right? And it turns out that that is conserved in your product. So when we put these two things together, there's the six-membered ring that's formed. Here is my bridgehead carbon. It turns out that we are going to actually end up with two different positions for the electron withdrawing groups, right? If we were to draw this in the three-dimensional form, you would see one electron withdrawing group is down and one is up, right? I kind of screwed that up a little bit, but you get the idea, right? One is pointed down, one is pointed up. That's still an endo product, right? Because we still kind of fed Pac-Man with one of those. And so you will see that kind of conservation anytime you've got some sort of trans product. The electron withdrawing groups will end up trans as well. And of course, and I should have done this on the other one, right? You get an enantiomer of that thing, right? So, like in other words, like one group coming up and the other group going down, right? And so you get the mirror image of that thing. So that tells us a whole bunch about stereochemistry. Let me show you one example of something that is, instead of being a cyclic product here, is more similar to something that we saw in the introductory Diels-Alder videos. And I'll show you how I kind of think about stereochemistry. Okay, so let's say that I'm going along in the homework and I have to recognize my diene and then my dienophile, and I have to make sure that I keep track of stereochemistry in a product like this. Well, what you want to do is rotate about this bond, first of all. So what we'll end up with is something that looks like this, right? Because you have to make sure that you put it in that S-cis form. And then this thing, right, is going to have to feed the sandwich, so we're to rotate that thing around. Put the nitriles on this side, right? We'll show our, I guess we'll do red arrows here. show our arrows, like so. Almost lost track of my arrow there, which ultimately will give me my 6-membered ring. Right? Just by convention, I'm going to have those nitriles going back. And then, well, by the way, I could have shown them coming out, except that I would just, I would have to make sure that these groups always ended up on the same side as those things, right? So these guys right here, right? If those guys are going to be ultimately a dashed wedge, these have to be dashed wedges as well. Right? So it turns out that we would form this as the sole stereochemical product plus an enantiomer, of course. Right? In other words, the enantiomer. The other enantiomer is if I put those CN groups out there, like coming out of the board, I would have had to make both of these guys also coming out of the board. Right? So that's what I mean about like how important it is to see your cyclopentadiene, right? Have that kind of in your head. That always helped me to remind myself that whatever is kind of, in this position, right? In the inner position, that position, right? The inner position, that ends up on the opposite side. So if we had some other group here, let's just, for fun, we'll add it in green. Let's say that, I don't know, I had some not very bulky group, right? So like deuterium, because I don't want to slow down the Diels-Alder reaction, right? That deuterium would then be projecting out like this, right? And so hopefully this helps you to understand the stereochemistry of these things. Now we're going to switch over and we're going to talk about the regiochemistry of Diels-Alder reactions. Okay, so here are some just random other starting materials here. All right, we've got our diene, we've got our dienophile, and I arranged it somewhat like it's supposed to be arranged. And what you can tell now is if I were to draw arrows from this thing, right, I could either end up with a product where this was on position 3, right, in the new ring, or I could end up with flipping this entire thing over, and then that would end up in position 2. So it's really tough to see unless we just draw it. So let's draw the two possibilities, right? I could react exactly how I have these things situated, right? Which would have given me, as a product, something that looks like that, right? So a 1, 2, 3 product. And by the way, I'm ignoring stereochemistry. I guess I should probably show these things, right, on the same side like we just learned. Right? So, or I could have, plus an enantiomer, ignore that. Or I could have flipped this thing around, right? And so I'll just do that by erasing it, right? Or I could have ended up with that guy. I'll just write these up here, right? That's a 1, 2 product. And this is a 1, 3 product. And for reasons that your book will go into, there is a really nice resonance argument for explaining this. But I'm just going to tell you the truth. I'll tell you the truth just this one time, that it is often the case, in fact 99.9% of the time, 1, 3 products are not going to be possible in a Diels-Alder reaction, right? And that is kind of the one thing that I always memorized about Diels-Alder reactions. And the reasons for that come from like a resonance argument that your book does a really good job at describing, if I remember correctly. So in a case like this, right, where we could get a 1, 2 or a 1, 3 product, we only exclusively get the 1, 2 product in terms of regiochemistry, right, in terms of how the different substituents are organized. Of course, it's also stereo-specific, such that those two things have to end up on the very same side. Okay, so we're going to do the Diels-Alder reaction arrows, and one possibility would be to arrange everything just as I've arranged it. All right, might as well put this specifically going down there, plus it's an enantiomer. Or I could have flipped this thing around and ended up forming this product. Okay, so once again, we've got two different possibilities. This guy, once again, is a 1,3 product. This is a 1,4 product. And of course, we just memorized the fact that 1,3 products do not work in Diels-Alder reactions. It turns out that you will only get this, right? So that's why I memorized, right? You just don't ever get 1,3 products in a normal Diels-Alder reaction. So it's either going to be a 1,2 or it's going to be a 1,4. And of course, if we put two substituents out here, you don't have a choice, right? Those are both going to just end up on the ring, regardless. So, in that case, I guess you're kind of forcing a 1,3 product, but it has to be in conjunction with also like the 1,2 or the 1,4 kind of thing. So hopefully that didn't confuse you. Take a look at the homework for this week, and we should have the opportunity to show everything that we've learned. Thanks a lot.